Okay, so okay. So our problem is for 139. The question is like this. The loading on the bookshelf is distributed as shown. Determine the magnitude of the equivalent resultant location measured from point O. So we have a bookshelf. In fact, it's fixed to the wall at point A and O, and at another point, let's say that this point is D. Okay, so distance between A and O is given as 1 meters. And in fact, distance between A and D is given as 2 meters. There exists a distributed load acting on the wall. The magnitude of the distributed load is 30 newtons per meter up to a point of here, so which is 1.5 meters away from point A. And then the magnitude of the distributed load increases to 50 newtons per meter because of the books. Okay. Now, first, let's draw the beam first. We have here point O, it's fixed here, so there is another point here, and then we have another point here. Certainly we have a distributed load FR1 because of this 30 newtons per meter load, okay, and then we have FR2 because of the distributed load of 50 newtons per meter. So FR1 is equal to 30 multiplied by 1.5. This is the integral of this region, right? Because 30 newtons per meter load applies along a distance of 1.5 meters. As a result, it takes 45 newtons, as you see. Now we have this 50 newtons per meter load, distributed load. It acts along a distance of 0.5 meters. Then we multiply 50 by 0.5 and it gives us 25 newtons. In fact, both FR1 is magnitude of the FR1 is 45 newtons and magnitude of FR2 is 25 newtons. Since the load is distributed, it will act at the center, which is 0.75 meters. We will find it as well. And we can say that FR2 acts at the distance of 0.25 meters. Now, we have two loads and we can find their the resultant force generated by FR1 and FR2. In fact, it is the sum of these two. Since the magnitude of the resultant force will be the sum of Fr1 and Fr2. In fact, it will give us minus 70 J vector if X is along this direction and Y is vertical and X is horizontal. It will be minus 70 J. Now let's write the position vectors of Fr1 and Fr2. Fr1 acts at minus 0.25 I vector if we put the origin of the coordinate system at point O. Okay, and Fr2 will be 0.75 meters, so it is 0.75 I vector if we put the origin at point O. Now the moments generated by Fr1 is R1 vector product Fr2, and moment generated by Fr2 is R2 vector product Fr2. This basically means that minus 0.25 I multiplied by minus 45 J vector and 0.75 I vector multiplied by minus 25 J vector. Now from I to J, okay, so it's like this. I put my elbow on the x-axis and I curl my fingers towards the y. So I assume that the positive z-axis is towards me. It will make a positive k vector, and 25 multiplied by 45 will make 11.25 in fact. So these two minuses will make positive and I will have 11.25 k vector. And from here, from 75 I vector multiplied by minus 25 j vector, so I to j will be a positive k, right, in this case, and then I have a negative component, so 25, it makes 12.5, 18.75, and the resultant moment will be, in this case, minus 7.5 k vector. Now, the moment generated by the distributed load has to be equal to the moment generated by the resultant force. Now, I know the magnitude and direction of the resultant force. It is minus 70 j vector. In fact, let's say that the coordinate is x, I vector. Then I will have minus 70 x k vector has to be equal to minus 7.5 k vector. Now these two minuses will cancel each other. That's also okay. If I divide 7.5 to 70, I will have 107. Therefore, the resultant force is acting at 0.107 meters away from the origin. Basically, I can say that it is somewhere here. So this is where the resultant force is acting, x, and this is the magnitude of the resultant force.